today I written something that side. I cannot use the board, so I covered it. So I got some restricted space here. In case when I write this side, if it is not visible, tell me immediately. Anyway, I have taken care. Because full board is not there, partial board. Little bigger I will write. Okay, up to here there is no problem, I think. I'll check it. Up to there, if there is no problem, I will not go beyond that line. No, little this side further. Hello? Still not going. Here now. Now okay, I think. That line is visible. He's playing with me. Okay, I will manage with that space. Oh yes, I can write up to here, no problem. Okay, voice clear? Charging is on. I will check once again, safer side. Actually on. Still, sometime what happens, I think it is on. If it is not on, problem. No, actually no problem. Charging on. Display, etc. No problem. Okay. We start now. See, come to the most important part of the bending stress chapter. See, I will not waste time unnecessarily on these small questions. I will consider a critical question. Then, maybe tomorrow or day after tomorrow, what I will do is, I will write a series of questions. Before the class only, almost full board. Little smaller you can see. You can see in the laptop bigger. And I will explain all the questions. All are very easy. The typical or master question I am going to solve now. But before that, little theory is there. See, I won't write cross-section. Because now I will not show y1 more than y2 or y2 more than y1. That is not required. See, make a note. See, suppose the cross-section is like this. You make a note here. Cross-section like this. Center of gravity, usually CG, I use red color to show neutral axis. Usually Y, just to show it is neutral axis. See, neutral axis here. It will be straightly down. Make a note here. Whatever is there, this is your y1, this is your y2. Now I will not tell. See, I told you, what you are writing is a cross-section subjected to BMM. Cross-section subjected to BMM. See, very important. Subjected to means forced. Like money matter once again. You went somewhere and spent. You went to a restaurant and whatever you want, you fully consumed. You ordered and enjoyed the food. Time has come for the bill. It does not matter, or the person who is preparing the bill will never ask you, have you got money, can you pay the bill? He will prepare the bill and give you. Same way. If you apply it, these all you have to write, remember, I cannot keep on repeating. If you apply a bending moment, see what I am doing. I will take the beam, some cross section is there, I will apply bending moment. See, I applied. Sagging or hogging, I applied bending moment. Now, I am not bothered whether it can resist it or not, whether the stresses developed are within the limit or beyond the limit. Nothing I am bothered. Simply apply. Simply go and eat. Write these things, no problem. People may tell, eating is coming in bending stress. If you want to understand, it will come. Simply go and eat. Wait for the bill. Here, see what happens. That's all. Now, see, I will explain last time. Bending stress distribution, will see, this is the neutral axis. Now, suppose the this what you are writing here, what I am writing is bending stress distribution across cross section. You write if you want. Maximum at the extreme fiber, 0 at neutral axis, linear variation. One side compression, one side tension. Those who are serious will write it. So I am not writing now. Okay, now suppose the BM is sagging. Then neutral layer comes here. See, when I show sagging, I am writing lengthwise sketch. This is actually cross section. This red line will come this way as neutral axis. See, this red line is the lengthwise. And when you take cross section, you can see the corresponding intersection line here. That plane with cross section, that is neutral axis. So this is actually where? This is, see, this way over. Then top will be compression, bottom tension, stress diagram will come this way. Whatever is there, I call the sigma 1, I call the sigma 2. Irrespective of sagging or hogging, I always call, I think, is it visible or is it partially not visible? Shall I make little down? 1 minute. Shall I make little down? I think I cannot see it here. Partially not visible. Okay, 1 minute. I will push little down because I can see, you cannot see the top written. Yes, little down. Okay. I cannot move sideways. That is the problem. See. That moment of inertia you cannot see. I will write once again that one. Okay, I will cover that I value. Okay, now no problem, I think. See. Now there is no problem, I think. It will come down. Yes. Now okay, don't worry about I value. I will write, I can see it. Now fully clear. Okay. Now fully clear. Everything I am going to tell now, make a note. If you want complete control on this chapter. And remember, I am going for serious question. This question will take 2 classes, not 1 class. Because I am going for different possibilities of moment of resistance here. Unsymmetrical chosen because it will give you concept much more than symmetrical. Once you solve unsymmetrical and get the complete concept, symmetrical is very easy. Meanwhile, to understand some money matter example, I will give you. So many people know it, what I am giving. Okay, see, sigma 1. If it is sagging BM, then the sigma 1 is maximum compressive stress. Sigma 2 is maximum tensile stress. Why? Upper side compression, lower side tension. I repeatedly told you, it is not like this. This compression is perpendicular to the cross section. Told repeatedly earlier. You actually should turn this way. So if I put an arrow mark here, compression, it is actually this way. Now I will not tell. See, this way it is acting. But I cannot write the diagram here. So I am folding it here. Okay, now. By chance, if the BM is hogging, see, if the M is sagging over, if M is hogging, then top will be tension, bottom compression, neutral layer here. Then I will do, usually what I will do is, I will plot tension left side, compression right side. See, then this is sigma 1 only. Sigma 1 is not tension compression. Sigma 1 in my class is topmost fiber stress. Sigma 1, this is sigma 2. It will come this way. Okay, straight line. Okay, no problem. Some will start commenting. Little curvature. Don't see that one. Tension compression. Now this will be maximum tension. This will the sigma 2 will be maximum compression. These are the extreme fiber stresses for section. Now, in this section, see, just imagine this is your Y1, this is Y2. Just to understand, imagine Y1 is more than Y2. Just imagine. But don't by heart. If Y1 is more than Y2, top everything you are right. What I am telling today, finally it may become 10 pages for you. Write each and everything. After the class over, go through the class, slowly write it. See, if Y1 is more than Y2, then neutral axis somewhat down. That is, if you come to mid height, it will come below the mid height. Suppose the height is 400, it will come more than 200. In that case, topmost fiber will be at more distance than bottommost fiber. Therefore, if y1 is more than y2, irrespective of sagging or hogging, tell what will happen? What will happen? Your sigma 1 will be more than sigma 2. Clear? Yes or no? See, you can see here. Here y equal to y1. See, when you put the stress calculation formula, sigma in general, m by I into y. So, for stress sigma 1, put y equal to y1. For stress sigma 2, put y equal to y2. If y1 is more than y2, your sigma 1 is going to be more than sigma 2. Clear? I will not repeat. Everything you have to write. Okay. That means, right here, that means if the BM is sagging, then when y1 becomes more than y2, tell me, maximum bending stress will be in compression or tension. Where maximum stress will come? See here, if the BM is sagging, see whether it is sagging or hogging, irrespective of that one. If y1 is more than y2, sigma 1 more than sigma 2. Okay, now, if the BM is sagging, sigma 1 more than sigma 2 means here, due to bending, stress will be maximum on compression side or tension side. First, anybody on the road can tell, compression side. Then, maximum compressive stress, sufficient, you write, compressive stress is more than maximum tensile stress. Write correctly, over. Whereas, if the BM is hogging in nature, then also sigma 1 is more than sigma 2 only. Then, see, when irrespective of sagging more, maximum compression is sigma 1, tension is sigma 2. See, or no, sigma sufficient. If the BM is hogging, even then also sigma 1 more than sigma 2. Why? To decide sigma 1 more than sigma 2, we never bother tension compression. Then, tell the answer. Maximum, which is more? Compression more or tension more? If the BM is hogging, which more then? If the BM is hogging, which is more? Maximum tension or maximum tensile stress, sigma means stress, is more than maximum compressive stress. One note right here. Now, go for a reverse calculation. I will not write anything on the board. You should prepare this chart. See, or suppose the cross section is like this. See, this way. Imagine neutral axis comes here. Now, here, this is y1, this is y2. This is neutral axis. And just imagine your y2 is more than y1. Means from the neutral axis to the extreme fiber, more distance for bottom fiber than top fiber. Then, undoubtedly, see, when you draw stress diagram, sagging means this way. See, if sagging means top compression, bottom tension, it will come like this. Sigma 1 here, sigma 2 here, compression tension. Or, this is if sagging. Or, if hogging, top tension, bottom compression. Even then, sigma 1 I will put this side, sigma 2 here. Okay, now, neutral axis, okay. Now, this is tension compression. Irrespective of hogging or sagging, now, tell me, which is more? If your y2 is more than y1, undoubtedly, bottom fiber stress more or top fiber stress more. y2 is more than y1, then undoubtedly, don't tell tension compression. Bottom fiber stress more or top fiber stress more. Among the two, both are respectively maximum only. One of them is maximum compression, other is maximum tension. Bottom fiber is more. See, bottom fiber more. So, your sigma 2 more than sigma 1, irrespective of sagging, hogging. Now, if the BM is sagging, then what? Maximum stress, maximum tensile stress will be more than maximum compressive stress. Or if the BM is hogging, then sigma 2 is more than sigma 1. Maximum compression is more than maximum tension. So do not by heart that sigma 1 more than sigma 2 means tension compression. That depends upon the bending moment nature. Don't call bending moment clockwise, anti-clockwise. Now imagine people calling clockwise bending moment, anti-clockwise bending moment. What they tell? The beam is subjected to clockwise bending moment. What? Now only you can see, if you tell clockwise bending moment, anti-clockwise bending moment, how ugly it looks like. Agreed or not? How ugly it is to call bending moment clockwise, anti-clockwise. It looks really ugly. If some are getting hurt, let them get hurt. Why? Because they are using something nonsense for that one. Okay. Now, see, you tell sagging or hogging. See, right side force, compression, nonsense. If I have a member here, right side force will create compression. If I put the member this way, same right side force will create tension. So you don't call axial force as right side, left side. You call tension compression. Bending, call sagging, hogging. Okay, leave it now. Now make all these note. Now I will go to, that's all. Now I am not going to repeat all these once again in this class. So when I go for moment of resistance calculation, little later, when I go for it, see, there are one typical example I am solving. When I go to that MR calculation, these things I will not tell. You should tell where maximum stress will come. Will it come in compression or tension, depending on the bending moment or nature of bending moment. Okay. Now, this much theory told, I'll remove all this one now. Correctly make a note of this one. Now, more powerful concepts. 1 minute now, little. I found a new cloth for easy rubbing. It rubs a little faster than usual paper. Especially little dry, wet it is. But I can make it immediately dry. Invention always, some invention. Where is the paper? It's here. To make it dry, I had to wipe with a dry cloth. Okay. Now, see, now I will do one thing. I will not draw the diagram. So don't by heart sigma 1 more than sigma 2 or sigma 2 more than sigma 1, y1 more than y2, y2 more than y1. Sometime y1 can be equal to y2. Make a note. In case you will make a note. I am not writing on the board. Okay, I'll write. Suppose cross section is symmetrical, like rectangular section. See, neutral axis comes exactly midpoint. Then, if the total depth is d, d should be black color. If the total depth is capital D, then each will be equal to d by 2 and d by 2. Then, bending stress diagram will be like this. Compression here, tension here for sagging BM, or tension here, compression here for hogging BM. This is sigma 1, this is sigma 2, sigma 1, this is sigma 2, sigma 2. This is the maximum compression, maximum tension, maximum tension, maximum compression. Now, since your y upper side is equal to y lower side, your y1 equal to y2 equal to d by 2, your sigma 1 will be equal to sigma 2. Therefore, irrespective of sagging or hogging BM, maximum stresses will be at the extreme fiber. How much is the maximum compression? Same will be maximum tension. If the BM is sagging, maximum compression at the top fiber, same maximum value as is tension at the bottom fiber. Or if the BM is hogging, maximum tensile stress at the top fiber, how much maximum? Same value, maximum compression at the bottom fiber. Clear now? This sheet is not clear means there is no point in taking class further. This also clear? This is symmetrical section. Okay. Now, why I am telling all this? Because when you go to MR, moment of resistance, especially for unsymmetrical, symmetric also concept is there. Especially when you go to unsymmetrical section, then there are going to be little extra concept. Delicate concepts are there. Once you get that concept clear, this chapter becomes almost closed. I won't waste time here wasting unnecessary questions. What practical knowledge required or what knowledge you require for basic understanding, get it. Then you can study any question. Suppose you are studying for IAS or IES or GATE. Understand the basic. Then any question you can understand. Okay, start. Now, see, consider the equation. M by I equal to sigma by y. Here, remember, this is the general equation. General equation can be used to find bending stress anywhere across the cross section. That means if the cross section is something like this, don't tell y1 more y2. Suppose imagine neutral axis here, make a note. Then you can find stress here, you can find stress here, you can find stress at this level or stress at this level. Actually everywhere same stress. You can find stress neutral axis, stress here or stress here. See, across the cross section, I will put points as top extreme, bottom extreme B, then upper side some level P1, lower level some level P2. P means point. It is not point. Level. Okay. Level 1. Level 1 meter. See, this is your Y1. This is your Y2. I will do one thing here. Randomly I will put level 1 dash, level 2 dash. Now, imagine this is your Y1 dash. This is your Y2 dash. Topmost is Y1, bottom is Y2. Your bending stress diagram is like this. Now, sigma 1, sigma 2. To get sigma 1, you put y equal to write, not arrow mark. You should write there. When you make a fair copy, write there. Right here. To get sigma 1, substitute y equal to y1. To get sigma 2, substitute y equal to y2. To get stress here, sigma 1 dash, level 1 dash. What you do? Substitute y equal to y1 dash. To get the stress here, somewhere here, sigma 2 dash, substitute y equal to y2 dash. You can do that way, or you can do right here. If I want stress at top fiber, see general equation. This is anywhere across cross section. Y is, I told you, sigma is bending stress. Anywhere, no restriction, anywhere across cross section at y from neutral axis. This red is not neutral axis. Important statement. Again, due to BMM, to which cross section is subjected to. Like what? You ate something. Somebody takes a full food, maximum bill. Somebody will take coffee and tea or light one idli or vada. That's all. Lesser bill for him. Somebody will go inside, sit for 5 minutes, drink water and come out. No bill for him. Neutral axis. No bill. So as you eat more, bill will be more. As you go away and away from neutral axis, your stress will come more. Okay. Now, so right, you can find anywhere. What you require is across the cross section, including extreme fiber. M by I sigma by y, put y wherever you want, corresponding to level across the cross section, get the bending stress there, based on sagging or hogging, decide tension or compression. Okay, now, but if you want somewhere in between, what you do? You use the same equation. You write y equal to y from neutral axis up to there only. It is this y1 dash is less than y1. This y2 dash less than y2. That is one of the option. Other option, I will not tell once again. Since variation is linear, by chance, if you know extreme fiber stresses, you can find stress anywhere across cross section using what? Tell me. If you know sigma 1 and sigma 2, suppose a question given, it is given sometimes in objective questions. They will tell maximum bending stress in compression is so and so. What is the stress max tension at so and so? Some will tell bending moment not given. I forgot right here. I is moment of inertia. I am not writing. Not writing. Okay. Now, then they will get confusion. Bending moment not given. I not given. Not required. Why? If they give the extreme fiber stress, you can find stress anywhere you want because it is linear variation using what? Tell me. If you want using similar triangles, you can get it over. But remember that you cannot do for shear stress. Why reason? Anybody can tell? Suppose the shear stress distribution, little later it will come, not now. If you go for shear stress distribution, you cannot do it because the variation across cross section is not linear, it is parabolic of second degree. So therefore, here over. This is also a clear concept. Remember, this is due to bending moment M. I told you, like you eat and get the bill. When the bill comes, it has nothing to do with your capacity. He will not ask you how much money you have got. Same way, if I take a beam, apply a bending moment, stresses will come. Somebody will ask, permissible? I don't know permissible. You apply this beam and Kannadadalli, Madidunno Maharaya. Hindi, Jaise karo, vaise baro, something like that. As you, whatever you do for it, penalty or get punished for it. Apply BM, stress will come. Be careful. When you put M is the bending moment, remember, when you put M as is the bending moment applied for cross section, I'll write here. Therefore, conclusion, in the equation, M by I equal to sigma by Y. If you substitute M as the bending moment to which cross section is subjected to, or how much bending moment is applied for the cross section, then sigma gives you how much stress developed, how much stress is developed where? Anywhere at Y, developed due to that applied BM. Here, permissible, allowed, material property or strong, weak in tension, weak in compression, whether it can take the bend stresses or is it safe or unsafe, none of them counts. You eat, pay the bill. They will tell, I cannot pay the bill. Then why you ordered the food? Sorry, they will tell, nothing doing. See, or I will do one thing now. See, I will take one more beam now, apply a bending moment. See. You can see. Okay, see, some beam here, small beam here. I will apply bending moment. Okay, no problem. Oh, see, apply too much. Gone. Why gone? Because it was beyond the limit. So when you apply the BM, stress for that BM has nothing to do with the permissible stress, or it has nothing to do with the material. Whether it is what section is same for a given cross section. It can be of steel, it can be of timber, it can be of gold also, or rubber, or plastic, or anything, any material. For the cross section, see, there is no material property here. No material property here. How much is, see, when you eat in a hotel, he will not ask you, are you poor, are you rich, are you middle class, nothing. How much you have ordered, bill will come. This note firmly make here. For a given bending moment, when you find stress, it has nothing to do with the material. Why? What happened? What happened? You told adjusted. Okay. This statement I cannot. Okay, I will write what I will tell what I wrote here. Okay. Everything okay. This statement not visible, correct? Okay. I will write once again. I wrote here M is BM to which cross section is subjected to or applied BM. Here applied BM, then now visible fully, then what stress comes has nothing to do with whether it can take the stress or not. Is it safe or unsafe? What is the material? Is it steel, timber or gold? Even gold also will do, or anything. Nobody bothers. But remember that you have to bother when you go to moment of resistance, because their definition is moment of resistance of a cross section is the maximum bending moment which cross section can safely resist. See, for example, if you have 1,000 rupees with you, you go to a hotel and order food for 1,500. He will put the bill for 1,500. You cannot tell, I have only 1,000. Then he will tell, go to kitchen and do the work. He will not agree. Now, you should be careful. If you have 1,000 rupees in the pocket, that is the maximum money you can spend. That is your moment of resistance. You randomly eat what bill comes, that is not moment of resistance. Random bending moment. See, in RCC it happens. When you write equation for M, I always tell there it will give you stress developed irrespective of limit. But when you find MR, I use the term permissible stress or allowed stress. Now, concept clear? Everything you should write. This everything you should write to understand thoroughly. Little slowly I will go. I won't hurry. All concept clear now? What all I told, write each and everything. You will not lose anything. You will not lose. You will gain only. Someone will tell, these are all simple. Yes, simple. And one who tells simple, then he will only make mistakes. He will get, when you go to MR, he get confused. I will tell at that time why you have not noted down everything. Okay, now go to a conversion. See, now consider once again M by I equal to sigma by Y. I told you, you write once again here, where sigma is the bending stress at Y from neutral axis due to applied BM M, sagging or hogging. I is moment of inertia of the cross section about neutral axis. Therefore, you can tell sigma anywhere across cross section at Y from neutral axis equal to M divided by I into Y. This only will tell you, see, Y power 1, therefore linear. As Y, linear variation. As Y increases, stress will increase. Fully clear? I'll tell you why I am telling. Fully clear or not? Fully clear or not? M by I into Y. Fast comment, because I want to confirm that your voice is clear for you. There is no problem. Once in a while I confirm it. If I get a clear signal, I'll proceed. Sometime afterwards, some problem comes. What I talked is wasted. I do not want to waste my energy for nothing. Okay. Now, here, tell me, There are, see, M is the applied bending moment. There are how many section properties here? Tell me. See, how many sectional property are here? When you put sigma is M by I into Y, how many sectional properties are there? First, one or two. Properties connected with the cross section. One or two. Property connected with the cross section. One or two. Two. Why? Because I and Y both are cross-sectional properties. Okay. Therefore, I is moment of inertia of the cross-section about neutral axis. Y is distance across the depth of the beam or distance from neutral axis for the cross-section to that level or fiber where bending stress required. Now, two are there, no problem. Now what you can do is, you can rewrite the equation as sigma equal to M divided by I divided by Y. No problem. M divided by I divided by Y. Or you can tell sigma equal to M divided by the ratio of moment of inertia. See, as the moment of inertia becomes more and more, now one thing you remember, start, 1 minute. Why don't bother? Why is the where you want stress? That is not important. See, that means as the bending moment is more and more, good or bad? Tell me. As bending moment is more and more, good or bad? Common sense. Some will tell, what is that good and bad? I will tell my students know it. When I tell good or bad, they know it. What is good or bad? As the BM becomes more and more, good or bad? Common sense. Good or? Good bending moment more means good. What is this? Then I will apply severe bend. How? How bending moment more is good? Bending moment is like eating. You are spending. Bending moment good. How idea came? Bending moment is bad. Why? As the beam section is subjected to more and more bending moment, there is a chance of failure. Bending moment is bad. Okay, bad. M is bad. Or as M increases, stress also will increase. Bad. What about I? I is moment of inertia. See, inertia means inertness, or it gives you resistance. I is good or bad? As I increases, see here, as I increases, stress will become lesser. So I is good or bad? I is extremely good. It is welcome. I is good. Therefore, here I is the, in the complete structural engineering, make a note. Area A, not now, later you require it. See, make a note here. Area A, moment of inertia I, little later, one more term called section modulus will come, Z. Little later, when you go to column, one more term will come, radius of gyration, R. These are all, tell me, good or bad? Area more means higher cross section. I more means higher moment of inertia. Z more means once again higher moment of inertia. R means again higher moment of inertia. Therefore, area, sectional property, area, moment of inertia, section modulus, or later radius of gyration will tell you how much away it is dispersed. More and more dispersed away means stronger. So these are all good or bad? These are all good or bad? Hope he will fall down and break his leg. Somebody is doing wheelie here. I sincerely hope he will fall down and leg is broken. Okay. These are all actually very, very good. Or make a note, all these are strength supporting factor or strength destructive factor. All these are strength supporting factor. Hey, very good. Or strength destructive factors. My simple word. I use that way. Strength supporting means welcome. Strength destructive means no, not welcome. They are all strength supporting factor or strength destructive factor. Strength supporting factor. Okay. Now, bending moment is bad. Shear force is bad. Axial force is bad. Remember, bending moment applied is bad. But moment of resistance is good. Moment of resistance is how much it can resist. See, how much money you spend is bad. How much you can spend is good. Clear now? How much money you are spending is bad. But if you calculate how much money you can spend, it is good. Clear or not? Money which you are spending is bad. But if you calculate same money, how much money you can spend is good. Like spending is bad, money. Earning is good, that also is money only. Spending is you are losing it. Earning means you are accumulating it. So therefore M is bad. MR is not bad. MR is good. Why? MR will tell you how much BM, its cross section, can resist. How much money you can spend. This is also clear. So just because M, don't always tell bad. Applying BM is bad. Spending money is bad. But earning money is good. MR is like earning. You are earning the strength. Okay. Now, I stopped here. Now I by Y. The term I by Y, that is ratio of moment of inertia of cross section about neutral axis to distance of element or fiber from neutral axis. That ratio I is linear power 4, Y is linear, is called section modulus. Is called section modulus. Now tell me, can I use section modulus for intermediate fiber? Tell me. Extreme fiber, see now, to get top, see, if I put here now, suppose bending stress is this way, this is sigma 1, sigma 2, then see here, when you put M by I equal to sigma by Y, your sigma or sigma equal to M by I into Y. If I want sigma 1, it is M by I into Y1 or M by I divided by Y1. This I will call M by Z1. See, that is called Z, section modulus Z. Same way, sigma 2 equal to M by I into Y2 equal to M by I divided by Y2. This I by Y2 I will call Z2, M by Z2. Here, Z1 is I by Y1, Z2 is I by Y2. Over. Clear now? Z1 is I by Y1, Z1 is section modulus with respect to top fiber stress. And I write once again, Z2 is section modulus with respect to bottom fiber stress. Can I use section modulus for intermediate level stress? Tell me. Can I use section modulus for intermediate level stress? First. Can I use section modulus for intermediate level stress? Not extreme fiber. Intermediate level. Interior element. Can I use? Fast. Can I use? Tell fast. Why no answer? Can I use section modulus theory for interior fiber stress, not exterior fiber? If I want top fiber, put M by Z1. Z1 equal to I by Y1. If I want sigma 2, write M by Z2. Z2 equal to I by Y2. Why no answer? Can I use section modulus for somewhere here or somewhere here? Fast answer. See, no answer from you. You tell whatever you feel.
M by Z.
If it is wrong, I am there to correct it. In my class, you need not bother whether you are telling correct or wrong. After all, you are getting, I am making you to make them, sometimes I trap you to make the mistake. What is there? Between you and me, difference is there. Yes, sir, no. Yes and no, both answer. If somebody will ask me, can you use section modulus for the stress here? I will tell both yes and no. He will tell, what do you mean by that one? Wait 1 minute. Suppose you define section modulus exclusively for extreme fiber. That is what universally done. Universally, nobody uses section modulus for a random, see, then there are infinite number of levels. Each and every level, you cannot define section modulus. Standard is section modulus with respect to sigma 1, that is Z1, section modulus with respect to sigma 2, that is Z2, Z1 equal to I by Y1, Z2 equal to I by Y2. That is throughout the world universally standard. But that extreme fiber Z value, Z1, Z2, you cannot use for this stress. If you want here, you have to use Z1 dash. If I want this stress here, sigma dash, I have to use Z1 dash equal to I by Y dash. See, I by Y dash. Nobody will use that way because there are infinite points are there. Extreme fibers are unique. They are always unique. Therefore, section modulus theory you can use. If someone will tell me, you cannot use, I will tell I will use. How? I will calculate Z with this stress is I by this Y. He will tell, no, Z means I by extreme Y. Who told you? I am taking M by I equal to sigma by Y. I will take that particular Y. Okay, yes. Then I will tell him, don't use. Why? That is, looks very odd. See, intermediate, there are so infinite levels. So remember now, make a note. Section modulus approach, Z approach, use only for, tell me what? Section modulus approach, use only for, which one? Now we come to practical. That is, I am writing universally adopted. Universally adopted. Correct, it is correct. Intermediate, suppose someone will ask you, section modulus top fiber, I can tell the answer. Somewhere down, where I am not telling, then I cannot tell. Top fiber, he don't have to tell. So when there is a suspense is there, it is not used. Section modulus approach Z, use only for extreme fiber stresses. Extreme fiber stresses. Never use for any intermediate level stress. Or make a note here. See, last note. If extreme fiber stresses are required, actually this is the most important. Tell why. In bending stress chapter, most important is extreme fiber because they are either maximum compression or maximum tension. We always want maximum stress. When you want to check the safety or decide the strength, or your concern is always maximum stress. Clear now? Your concern is always maximum stress. So when you use the maximum stress, then use either basic equation or section modulus approach or section modulus approach. Okay. Basic equation is M by I equal to sigma by Y. Okay. This can be used for anywhere. Here, write Y equal to Y1, get sigma 1, Y equal to Y2, get sigma 2. Or you can use section modulus approach where your sigma 1 equal to m by z1, sigma 2 equal to m by z2. Z1 is section modulus for the cross section with respect to top fiber stress, top extreme fiber stress, and Z1 equal to I divided by Y1. Y1 is distance of top extreme fiber stress from neutral axis. Now Z2 is, I am not writing, those who are serious write, I will dictate. Section modulus for cross section with respect to bottom extreme fiber stress. Z2 equal to I by Y2. Y2 is distance of bottommost fiber or bottom extreme fiber from neutral axis. So if your interest is either the topmost fiber stress or bottommost fiber stress, either you can use basic equation m by I equal to sigma by y, or sigma equal to m by I into y. In here only you can make out, put y equal to y1 or y2, or you can use section modulus theory, z1 equal to m by z1, z2 equal to m by z2, then directly bending stress. See, general equation bending stress is bending moment divided by I into y. If you section modulus directly, bending moment divided by section modulus. This only will tell you section modulus is good. Why? As section modulus increases, tell what happens, tell me. As section modulus increases, stress will become. This only will tell you Z is good, because as section modulus for a beam increases, that is because of higher moment of inertia. Stress will decrease, good or bad. Stress will decrease, good or bad. Your stress is coming lesser for a beam in your building, good or bad. Basic and section modulus both are same. Yes, both are same. Sigma equal to m by I divided by y, I by y1 is sigma 1 z1. Both are same. Both are same only. There is if I solve the problem by basic equation or section modulus, I am not going to check the answer. It has to come same. Like see, if I solve a problem by moment distribution method, I will solve the same problem by slope deflection method. Actually, they are also same. To be frank with you, moment distribution, slope deflection and Carney's method all are same methods. But if I solve by column energy method, then answer will tally if method is correct. In my class, it will tally. Not a single problem in my class gave different answer when I solve by force method or displacement method or stiffness method or flexibility method. Answer never came different. But here I will not tell because both are same. Instead of writing 10 by 2, you are using 5. That's all. Divide by 10 into 2, I am writing divide by 5. Both are same. Okay, now, so make a note. I am not telling once again now. Last warning. If you are interested in the extreme fiber bending stresses or maximum bending stresses, either compression or tension, then either use basic equation, that is sigma equal to m by I into y, or sigma equal to m by z. To get sigma 1, put y equal to y1. If to get z, sigma 1, write z1. Z1 is I by y1. Sigma 2 equal to m by I into y2, or sigma 2 equal to m by z2, z2 equal to I by y2. So in our class now onwards, we will use section modulus only and only for extreme fiber stress. Only and only and only for extreme fiber stress. Clear now? Fast. Only and only and only for extreme fiber stress. We will not use it for stress anywhere in between. You can use, then that Z is varying. For to answer that Z, they should tell where they want. See, to find extreme fiber, they don't have tell where. The moment cross section is fixed, Y1, Y2 are obtained, Z1, Z2 is fixed. But other Z, you cannot decide. Depends upon where you want. See, if you start in a bus, if you sit in a bus, if you get down in the last stop, you don't have to ask anybody, is the stop coming, is the stop coming, where I have to get down? Nothing. You sit there. Last stop, conductor will tell, hey you, come on, clear off. In metro, if you don't get up in the last stop, they always come inside, tell, sir, over sir, get down. Now you are taking U-turn. Last stop if you are going, extreme values, you don't have to ask anybody. Sit there, final stop. But if you are getting in between, then keep on inquiring. Suppose you get up in Majestic and you want to go to Kengeri now, in metro. If you are going to Kengeri, you don't ask anybody. When the train stops, guard will come and see everybody. He will tell, sir, please, over. If you want to get down somewhere else, keep on looking at the observation or ask somebody, Vijayanagar, Banta, Eshdura ide. Suddenly you tell, sir, next stop Vijayanagar. See, that way. Clear? Z concept you use only for extreme fibers. But you can also see the board for extreme fiber. If you get in Kengeri, not extreme, you can see the board there when it shows this is Kengeri, get down. Or that is sigma equal to m by I into y. Or what you can do? When the train stops, when nobody is there, all are going, you also go. Very much tempted to do SA2 in detail, sir. Yes, yes. SK2 to a limited extent we are doing. Not practical, not academic oriented. All the basic concept, MD method, SD method, Kani's method, yes, I am covering. I committed. Yes, I am covering. Very much, but not YouTube, back in Zoom. After bending stress is over, I am going back to Zoom. Only this bending stress part is universal for public. Then again Zoom class only, not this class. SA2, see, your complete course, that indeterminate structure, determinate structure, and then consistent deformation method, how you analyze, or displacement method, MDSD and Kani's method, they are not much, because I will solve limited question. I will give full concept there. Not just tell you add the two values, divide by 2, carry over half there, or write the equation MAB equal M bar AB plus 2EI by L into theta A plus theta B plus or minus 3 delta by L, or Carney's method, what? Rotation factor equal minus half into stiffness of that member by sum of stiffness of all members. Not that way. I will tell the meaning of each one and see that everything is clear. I will give the link between the three methods there. You will agree. Oh, you will tell SD method, MD method, Kani's method. All three are same. You will tell at that time. But not YouTube, in Zoom class only. As soon as bending test is over, YouTube I am closing. Okay, now make this note. Now make second note. I am not repeating once again. I am not repeating once again. Second note. Second note in a small box. By chance, we have to find bending stresses anywhere inside, not extreme fiber. Means you write here. Or cross section. Okay. Somewhere here or somewhere here. Here. Then do not use Z concept. Actually you can use put Z equal to I by that Y. That will keep on. No, don't use it. We are not using. Do not use Z concept for intermediate level. Use the basic equation sigma equal to m by I into y. Wherever you want sigma, put that respective y value. Y is the distance from neutral axis to that level or that element where bending stress required. One, or by chance, if you already got the extreme fiber stress, you can find anywhere in between, because linear variation by using similar triangles also you can do it. Make a note, clear? Do not use Z concept for intermediate level. Inner 5 elements. Extreme fiber, either use Z concept or use basic. Both are same. But correct concept is Z concept. See, in RCC, you write mu by FCK into BD square. Heard of it? Tell me, this BD square actually connected with, and in bending moment, see, mu limit equal to 0.36 into FCK into 1 minus 0.36 into, I would other way, into XU max by D into bracket 1 minus 0.42 XU max by D into BD square into FCK. That BD square, this is actually connected with what? Tell me. You will know later that BD square is connected with what? Tell me answer. In RCC, that BD square is connected with what? Unknowingly. Unknowingly, not to me. For me, it is not. So many times I tell. Unknowingly, then I will tell. Unknowingly for you, then somewhere, what about me? Not for me. If it is unknowingly for me, I won't talk about it. So, see, if section is rectangular section, your I by Y will become BD cube by 12 divided by D by 2. It becomes BD square by 6. So, variable is BD square. 6 will come some, for RCC it is not 6 because lever arm is different. But this is number. So, finally, rectangular section, your Z is proportional to BD square. See, in RCC also BD square, in steel also BD square, everywhere it is BD square only. Breadth into depth square. That clearly shows breadth increases means strength linearly increases. Depth increases means it will increase as per the square. As per the square. If depth becomes double, strength becomes 4 times, not 2 times. Or it will increase by 3 times, reach 4 times. That I will tell you later. All these concepts, make a note. Now, non-stop I talked. So, not a break. Now, next part, see, right here. Next, I have to go to the most powerful term. Most powerful term. The very purpose of this bending stress chapter for practical design is, tell what? The most powerful term or the very purpose of this chapter for practical design. What? Tell me. The most powerful term for practical design. See, RCC, you call MU limit. We know that what? MU limit. Limiting moment of resistance for rectangular balance section. In steel, see, you got bending strength equal to what? Sigma, what is symbol? I forgot name only. It is not sigma there. FB, I don't know FB. Now see, I forgot symbols only. Into Z will be there. So, or beta B Fy Zp by gamma MO, or 1.2 Zd Fy by gamma MO, or strength of a column, etc., etc. Not deflection. Sorry. What we discussed is how to find the stress produced due to bending moment. If you eat something, how much you have to pay? Now, not that way. How much you can eat, or what is your capacity? Tell the name. Now tell the name. Deflection later, not now. Now you are going for capacity. No. Technical term for capacity. Moment resisting. Oh, I am telling the answer only. How much BM cross section can safely resist the maximum capacity so that stresses are not beyond the permissible limit. There is a name for that one. It is called What? It is called what? How much BM cross, how much money you can spend. That is called moment of resistance, MR. For MR, what I will do is, in my class example, I wrote a section here. This section, first round today, I am using for stress calculation. Second round today, not today, tomorrow, I am using for MR calculation. So tomorrow's class, whether I do MR, basic property will remain same. Okay, now, write a note here. MR he will discuss after the stress developed part is over. So now, we will go for example. Remember, for example for finding stresses developed due to applied bending moment, or when cross section is subjected to a bending moment. Remember, bending moment is random. You simply ordered something without knowing cost. That way, that will go now. 1 minute. What is this one? As the 360. Okay, now take the example, class example. Example in the class. Right, I will give a question now. I am dictating, you should write. A beam cross section is subjected to a bending moment of 380 kilonewton meter. Without bothering, see, simply take a beam, apply bending moment. The beam may be weeping. Hey, I cannot resist it. I am going to break. Break then. I am not bothered. Tomorrow, no breaking. Tomorrow, you ask the beam, hello, how are you? How are you? Sir, I am fine. Now, okay, little more. Stop. Please stop, sir. Sir, I reached my limit. Please do not apply more BM. That is MR. Tomorrow, you will go and as you eat, you calculate the bill simultaneously, and when the total bill payable almost reaches your money in the pocket, you stop eating and tell waiter bill. Today not that way. Simply go, order food. This one, that one, this one, that one. Somebody will tell, do you have money? I don't know. Then, okay, let me see later. If money is there, I will pay. If it is not there, I will create drama. I will act. Suddenly, I will become fainted. In one movie it happened. He ate something and fainted there. I don't know name. Most was Jaggesh movie, I think. He fainted. Then all lifted him and put him somewhere outside. That's all. They told to nobody asked him the bill. He simply fainted. Then, after some time, when nobody is there, silently walked, rubbing his stomach. He was going happily. Don't do it actually. I am not telling to do it. Very good trick, see. But it will not work out every time. You suddenly feel fainting, something like that. They are afraid because they will think something because of food. They will not ask the bill. So you tell, if I can pay, I will pay. Otherwise, I will create drama. Okay. Therefore, today we are not bothered. He applied a bending moment of 380 kilonewton meter, sagging bending moment. In the question told, a beam cross section is subjected to a sagging BM of, see horrible BM. See the scale, what happened? Deformed beyond the limit. See here, deformed beyond the limit. I should stretch it back now. Okay, now okay. Even now, it has lost its straightness now, I am sure. But no problem. 380 kilonewton meter. Then, further in the question given, the beam has I section. I section. Why? Because my first example is unsymmetrical I section, where moment of resistance you have to struggle. Lot of concept is there. If I make complete clear how to find MR for I section, unsymmetric I section, then any question you can solve. Then everything will be covered. Controlling top fiber, controlling bottom fiber. Tomorrow full non-stop MR. So today no MR. Apply the BM. I section. I section of, see now, top flange 300 mm by 20 mm. Bottom flange 250 mm by 30 mm. Web of thickness 12 mm. And depth of web 300. He told depth of web is 350. Therefore, anybody can tell me what is the overall depth later, not now. He told depth of web is 350. So what is the overall depth? Ayyo, adiki istu beka. What is depth of web? Overall depth 400. Okay, that you do later. Now, question is sketch bending stress distribution diagram across the cross section and indicate clearly the maximum compressive stress and maximum tensile stress developed for the cross section, and also find bending stresses at 100 mm inside 100 mm inside the top edge and bottom edge. From here come down by 100, from here also, here come down by 100, here go up by 100. So somewhere here, that is where you cannot use Z. That is the question. Okay. Can you write the question now? What I told, can you write the question? The cross section of a beam is subjected to bending moment of 380 kN sagging. Cross section is I section or top flange 300 mm by 20 mm, bottom flange 250 mm by 30 mm, web 12 mm by 350 mm. Sketch distribution of bending stress across the cross section and clearly indicate maximum compression and maximum tensile stress and where. And if free, find the bending stress in elements which are situated 100 mm inside of the extreme fibers. Question clear? First, see, there is no strength based now. Eat the food and pay the bill. Here, permissible will not come. Is the question clear? Is the question clear? First, you are not answering. Is the question clear or not means you are not answering. First. Is the question fully clear? See? Doubt comes to me, whether audible or not, or is there any problem? Sometimes, see, if there is a problem, if the voice is not clear, if it is not heard by you, my effort is wasted. I do not want it. No. I am asking, is the question clear or not? Clear. Okay. Now, what you have to do is, first do one thing. Solution. Irrespective of bending stress, where all they want, we always need moment of inertia I about neutral axis. So, first what you do is, you locate where is neutral axis and find moment of inertia of cross section about neutral axis. I wrote here. See, this is a cross section. Write need sketch. Then distance of CG from the bottom edge. This is not given. This is my calculation. You should get it. First. Get it. And also, I about neutral axis. It is not visible there. I got 514.132 10 to the power 6. I first want these values. See, today I will not explain because time problem. I will proceed further with this value. But tomorrow, for those people who are new and who are not having much idea, I will briefly explain location of CG and calculation of MI to how much I know. I am also got limitations. See, moment of inertia, how much I know, that much briefly. Tomorrow I will explain. Today, but I want confirmation from you, because tomorrow no one should tell that answer is wrong. So I will take 5 minutes break now for non-stop talking. I will take 5 minutes break and come back. By that time, those who know already, locate neutral axis and find I. See, from bottom fiber, I got 187.2. From top fiber, 212.8, and I got the I here. I want confirmation from you that these are correct value. This I calculated before the class. See, this I calculated before the class. Before starting clicking live, go live, I took the calculator and got the value to save the time. No, I want that confirmation that Y bar and I are correct. Yes, but still, you might have got it. I need some rest now, at least. I need 5 minutes rest. Okay, I will take 5 minutes rest now. Non-stop talking gives lot of strain actually. I will take 5 minutes rest. By that time, okay, some already got it. Others, try it now. I will come back in just 5 minutes. Just a minute. See, now I slightly are capable, if I and Y correct, you find Z1, Z2 and find sigma 1, sigma 2. Already some answers given. I'll check it later. Anyway, not explained by me. Someone told this answer. We'll check tomorrow. This value is maximum compressor at the top. How much? 157 point. 157.28 in the top fiber. Bottom is 138. Yes, 138.36 at the bottom. And here also, you come down by 100, get this value. Okay, now I decided something. Already getting 9 o'clock. Because next class I am going for MR. To correctly understand developed stress and moment of resistance stress, they are different. So to give analogy, tomorrow full board is there for me, no restriction. So therefore, I will enter the answer of this one this side with the calculation. Put one line here. Then I will tell, keep on looking there always. Now I will go to MR concept. I think instead of hurrying, better both of them if I do simultaneously. So you got the answer correctly. Tomorrow you can check. Those who are not getting, don't worry, I am covering. So today's class I will curtail now with the information for work for you, locate neutral axis and find moment of inertia. Tomorrow briefly I will write. I will do one thing tomorrow. Before the class I will put the cross section here, write the steps and explain it. I won't tell in front of you. Explain it so that it will benefit those who are not knowing about location of neutral axis and Y bar. Okay, done. So it is better to continue this question and get the stress and simultaneously get MR. So I feel your control will be more if you know both solutions simultaneously. This will not take much time. Sigma 1 equal to m by z1, sigma 2 equal to m by z2, or sigma 1 equal to m by I into y1, sigma 2 m by I into y2. Okay. This I will take a photo of this one now. Why? Because I am rubbing this one. I will write once again section. Okay. Tomorrow I will continue. I thought I will continue for 5-10 minutes. Then, no, I have to hurry. I thought, better tell both the concepts single time. It is much more better. People can understand then difference between what? How much you eat and pay the bill, or how much you can eat safely. They are different. Randomly eat, you have to pay for it. Or check the pocket and eat, that is safe. So tomorrow, direct effect of M will come, and also how to control the M, both will come tomorrow. Okay, thank you. Go through today's class repeatedly and everything I told, make note. Each and everything I told. I think some of you are already knowing it. If you are knowing it also, I told in the compact way. That compact way is important. Okay, we will meet tomorrow, same time. Thank you. Yes, bending stress and RCC are directly connected. See, there also same thing you are doing. For a given BM, you find the stress developed. Or you decide what is the balance section and under reinforce, over reinforce. Then you put the permissible stress. Then you get MR. Correct? They are directly linked. This all in RCC class I told you. See, in the RCC class, this all I told you earlier, if you remember. Applied BM, how to find stress, or material property, sigma CBC will come. See, when you find stress, sigma CBC will not come. Simply FC and FST will come. But when you find MR, then sigma CBC and sigma ST will come. I told some example, money matter. 1:10 ratio. If two people go for a food, if he pays 100 rupees, how much he has to pay? All that will come tomorrow. Repetition. Okay, thank you.